This is a work from Qualcomm AI research titled Boosting Neural Video Codecs by Exploiting Hierarchical Redundancy. The main principle in video compression algorithms is capturing redundancy in video pixels by reusing previously decoded pixels. Here we define two levels of redundancy in videos. The first order is the redundancy in pixel space, which is the similarities in pixel values across neighboring frames. Most of the existing video codecs are designed to capture this type of redundancy, and they do so by following a two-step process. 1. Motion compensation, and 2. Residual compensation, as shown in the block diagram. The transmitted motion and residual maps corresponding to the video sequence are shown here, and as can be seen, both these maps are highly correlated across time steps. This leads us to the second order redundancy, which is the redundancy in motion and residual maps. In this work, we introduce generic motion and residual predictors that capture second order redundancy by reusing previously decoded data. The predicted motion and residual maps and the corresponding transmitted motion and residual maps are shown here. As can be seen, the transmitted maps are much less correlated across time steps, which means we will need less bits to transmit them. It is worth noting that the prediction does not consume any bitrate. Here we show how our method works. The predictors that we present can be employed with most neural video codecs in order to improve their rate distortion performance. Here we build upon the well-known video codec, scale space flow, shown as base codec. A motion predictor and a residual predictor are added to the base codec to obtain the boosted codec. The motion predictor receives a history of input frames and previous motion maps and predicts the current motion map. Similarly, the residual predictor receives a history of previous motion compensated frames and predicts the current residual map. As noted before, the motion and residual maps in the boosted codec are less correlated compared to the ones in the base codec, resulting in overall bitrate saving. The network architecture used here is quite simple, as all the components in the network, including the motion and residual predictors and the motion and residual codecs, follow a simple autoencoder architecture. The default architecture that we use is for the RGB color space, as RGB is the dominant color space in neural video compression, since R, G, and B channels have the same resolution. However, since the YUV420 color space is highly adopted in the standard video compression community, we make simple modifications to the autoencoder's input and output heads with no further modifications to accommodate YUV420 videos. We use the Vimeo 90K dataset for training and train our codecs on sequences of 4 frames with a batch size of 8. We optimize the codecs on different bitrates using MSE and MSSIM distortion losses. We evaluate the models on the UVG, MCL-JCV, and HEVC Class B datasets and compare them with the state-of-the-art, as well as the standard video codecs. Here we show the rate distortion performance in terms of PSNR versus bits per pixel on the UVG dataset, where the base codec and the boosted codec are shown in purple and red respectively. We also measure BD rate saving of the boosted codec compared to the base codec on the 3 datasets, and the results reveal around 38% and 34% bitrate saving on the UVG datasets in the RGB and YUV420 color spaces respectively.